I guess I see that I missed a step, but I'll try to put this together in the right order. So one is used to seeing factors of volume appear in the entropy. Okay. In the black hole case, instead, what we see is the surface area of the black hole. So at the linguistic level, this word hologram relates to what you would have thought was a volume effect being replaced by an area. Okay. Now, to understand more the logic of why this is supposedly interesting, let me just remind you that it's very natural for black holes to have some kind of entropy. And why is that? Well, let's recall where entropy comes from in usual thermodynamics. Entropy comes from the fact that we don't know the detailed state of the system. Right? In usual thermodynamics, what we do is we say, aha, I know the total energy of the system, but I don't know the exact configuration of each of the little molecules of a gas. And then entropy, right, is the logarithm of the number of possible microstates which have that energy. Well, in a black hole, typically it's the same story. If you're sitting outside, you know the mass of the black hole because that determines its gravitational field, but you have no idea what happened inside because, as we said, you can't get any information out of the inside of a black hole. So it's very natural for black holes to have entropy. And one might think that it's natural for this black hole entropy. So let's see. I'll write this as a natural guess. Is simply the logarithm of the total number of states inside the black hole. In other words, it is perhaps natural that you should think of this entropy of a black hole as being the counting all things that could possibly go on inside. And you might say, if it's counting all things that could possibly go on inside, maybe that means that you should do this counting without even assuming it's a black hole. Maybe, this is again further guess, maybe this is in fact the logarithm of all possible states inside a region with area A. Okay. So some people look at this, and some people, the person who usually pushes this kind of thing hardest is Lenny Susskind. There are others as well, but I will not possibly remember to list all the right names, so I'll put down a 1, which is indicative. You can look up his papers on the subject if you're interested. So this suggests to people like Lenny that perhaps it's true that, in fact, the real possible ways that you can arrange things in some region of space scales like the area and not the volume.
Would that
yes?
be only positive energy states? Or?
Well, now that's an interesting question. The usual intuition here is that somehow it's all possible things. An excellent question. That is well, okay, good. So that is an excellent question. No one, excuse me, no one has a good answer to that question. Okay, but notice that's an issue with black hole entropy in general, and not an issue with holography per se. Okay, so in holography, people will say, well, there's some issue here which is very important that we sort out someday. Why is the number of states finite at all? But they jump ahead and they say, all right, let's take that as a given that it is finite through some mechanism we don't yet understand, and let's see what we can learn about other physics from that. Okay, so they say, all right, surely this, so they're guessing that in fact this number of possible states inside some region is also finite.
So why does that not hold for the box?
Because the box isn't big, because if you look at this logic, if this is to be true, most of the possible states associated with some region of space should be a black hole, if these two things are to be comparable. The box is not a black hole. We put that in by hand. So we've restricted ourselves to some tiny fraction of the possible states for a box. So the box would be a contradiction if the experimentally measured entropy of this box were larger than the entropy of a comparable black hole. But interestingly enough, that's not true. The black hole has much more entropy. So this is a plausible set of assumptions. Okay. Just to make one more thing clear, people in this business often talk about the entropy as counting what's called the number of degrees of freedom. Instead of saying it counts the log of the number of states. And just to give you a brief idea of what that means, imagine that we had n spins, each of which could take the value plus or minus 1/2. Okay? Well, so then one of these spins is something you would call a degree of freedom. It's something you can change about the system. Okay? And if I ask you, if I have n spins, each with 2 states, how many states are there for all n? Well, there are 2 to the n states, right? So therefore, the entropy is, roughly speaking, the log of 2 to the n log 2, whatever. So one often talks about the entropy as being proportional to the number of degrees of freedom. Okay. Similarly, suppose I had a box, and suppose I believed that this box was suppose I had, let's say for simplicity, a fermion field. So the electron field inside this box. Okay? And suppose I believed that field theory, our usual field description, is a useful description, but not at the tiniest scales. Because maybe I believe that space-time does something funny on very small scales. Maybe due to quantum gravity, something like that. So suppose I believe that field theory is a good description only for lengths bigger than some cutoff. This is the cutoff that Tony Z talked about. Okay? And now if I asked you how many states are inside this box, well, I could find out by starting to divide the box. I could make a little grid here, and I could divide the box into smaller boxes. Okay? But I'm only allowed to make the boxes so small. I can make the boxes of size LC. Okay? If I made them smaller, well, that's the cutoff. That's the smallest I'm allowed to make them. Okay? So there are therefore, in this thing, a large number of boxes. How many? Well, it's the volume divided by LC cubed. This is the fermion field. So roughly speaking, in each box, I can either have a particle or not have a particle. That's what we do with fermions. So the number of states is, again, 2 to the v over LC cubed. Or in other words, the entropy goes like the volume over LC cubed. Okay. And so this is where the great contrast comes in. The suggestion of holography is that somehow, due to gravity, due to black hole formation and so forth, the actual number of degrees of freedom in a box, again, scales not like the volume, but like the area. Okay? So the suggestion is that something that you would expect it to be 3-dimensional is actually 2-dimensional. And people might go on to further speculate that perhaps this could be true if some more fundamental description of our universe, including now gravity and its quantum effects, was actually something of lower dimension. That is to say, perhaps it's true that our universe is, as Lindy says, a hologram, or something that appears to be 3 space dimensions plus time, is better described as something that is only 2 space dimensions plus time. That's the basic idea of holography. Okay. I see that I'm rapidly approaching my the end of my time, but let me say just one more thing. Holography is a subject much talked about, and you will find many vocal enthusiasts of holography, especially in the string theory community. I have recently been going around giving a series of talks about why one might be skeptical about holography. Okay. It may well be true. I don't mean to prove that it's incorrect, but as I said, it's merely a set of suggestions. And there are also counter-arguments to believe that it may not be true. I have discovered while giving these talks that there is a larger set of people than one might expect who were already skeptical of holography, but were less vocal than those who were believers in holography, just to alert you. I don't know how to count the relative numbers of such people, but there are a fair number on both sides. And why might you be skeptical of holography? Well, let's simply recall that let's start by recalling that this logic here was not in any way ironclad. For example, let's start with the first statement. The first statement here was that was a guess that what you're counting for the black hole is the total number of states that could possibly be there inside the black hole. Okay? But recall that even for a black hole, we know something about what's going on inside because we, for example, know the mass of the black hole. So let's see if I can draw a picture. Even in a region inside the black hole, it's quite plausible that there are some things we could do in this region. Okay, there may be, well, I'll even say there are likely configurations of the inside with energy greater than mc squared. In other words, it seems quite plausible to me, at least, that there would be ways to set up the inside of a black hole, or the region of space. That is to say, it seems plausible to me that there are ways to set up the region of space inside a black hole, bounded by its surface area, which correspond not to the black hole one wanted, but to, for example, a larger black hole. And why not? That would be one way to avoid this series of holographic arguments. So anyway, this remains an interesting area of discussion and current research, and perhaps some of you will at some point be motivated to contribute to this discussion. In fact, I believe some of you already have in some sense. Good. All right. I am rapidly approaching the end of my hour. I think perhaps technically I have 4 minutes left, but let me stop here. This is a good point, and see if there are further questions. Nothing disproves anything here. So my only point was, here was a series of suggestive arguments, and I wish to simply point out what the possible loopholes are. So this was, the idea in this line of reasoning was that perhaps a black hole is what results when, as is often said, you excite some region of space as much as you possibly can.